then we'll move on to Brigitte Martini. Dr. Martini is currently the Chief Geologist and VP of Business Development for CORESCAN, a hyperspectral core imaging company and service provider out of Perth, Australia. She received her BS in Geology from the University of Arizona and a PhD from the University of California, Santa Cruz, with emphasis on the use of airborne hyperspectral imaging for resource assessment in volcanic systems. In the past 16 years, she has primarily worked in the resource sector, including geothermal, mining, and petroleum, as well as an academic and subject matter expert in hyperspectral and radar systems for the U.S. Air Force, Army, and Navy. I feel safer already.
You should. All right, good afternoon. Thanks for coming today. I'm going to try not to lose my voice here. This may become an interpretive dance. So today I'm here to talk to you about hyperspectral core imaging and how we apply that both in a huge scale. We're focusing in on exploration and how we can bring this into that arena. I'm of course going to hint, and there's going to be a logic to the fact that this gets brought in at an exploration level, but of course has huge implication down through the entire mine cycle, through the life of the development of an ore deposit. Of course, I'm also going to be showing you a lot of really finer images. You see that here we very specifically said exploration, mining, and research. So I'm also going to be showing a lot of pretty fundamental, amazing advances in spectroscopy that is now not only available to researchers, but then is actually being able to be applied in mining. So it's an exciting time for spectroscopy. I'll acknowledge very quickly a few of my co-authors here. Of course, we couldn't be showing you any of this without the assistance and the leap of faith that Dr. Anthony Harris took from Newcrest. So they were our early adopter, and the case study I'm going to be showing you today is the NAMOSI porphyry from Newcrest. And so it's with great thanks that we're able to actually show this today because of Anthony. And then my four other co-authors here from CORESCAN, Renelle Carey she's the head of our spectral geology team, and she's done all of the analysis that you'll see in this presentation today. And then these three gentlemen are the heart and guts and brains of CORESCAN, do the software, the engineering, the beautiful spectrometers, and all of the other things that make the CORESCAN system that I'm going to be showing you today. Just want to show you that along with this idea of showing you things that you've never seen before, I like to just sort of tease this a little bit here. There are things that we're going to show you that geologists are capable of, and there are things we're going to show you today that they're actually not capable of, and as a geologist, I'm okay with that. So, moving the mineralogical needle. What I mean by this is that in a very short amount of time, we've gone from looking at really fine scale things and doing a lot of really amazing new mineralogy, because that's really the theme of this talk today, is being able to do really good, accurate, consistent mineralogy. Things all the way from some of the new micro XRF systems, QuemScan, XRD, good old thin section, and being able to also then think about, there's that sort of traditional mineralogy, if you will, and then some of the more now moving into spectroscopy and being able to do the types of mineralogy we're able to do with that. So of course we start with point systems, like either the Express or ASD systems, the halos or the TerraSpecs, and being able to get out a single spectral signature there. And then moving up, so you're going from really fine scale, outcrop scale, and then moving up all the way up into the air and space. And so I'm not going to go through all of these, but these are just some nice examples of all the things, and Xiaodong just mentioned a few of them, that we've been able to do from air and space. But now there's a place in between that. There's a place in between space and outcrop, and that is core imaging. So if I just give you a quick example here, if you had a piece of core here, this is from a porphyry, you have a single point. That one single point here, you're going to get a single spectral signature out of that. We can then go to something like a line imager. So this is CSIRO's high logger that CORESCAN's just recently become involved with, and we'll be looking after. And instead of a single point, now you're getting a single line down the middle of a core. So now you start to get a much more complete idea of the mineralogy through the core. But now if we take this to a full imaging, we're now going to get not just what minerals might be present in there, but also now we start to get the textural component. I think that the image speaks for itself. plus you're going to get far more data coverage. 1 meter of core from the CORESCAN system gets about 200,000 spectra. So this is incredibly data rich as well. Okay, so I wanted to put a few slides in here. This is more from Anthony from Newcrest, sort of their vision of exploration and why you might want to do this. The exploration, he's basically pointing out here that everybody's seen this diagram, but the fact that the way that we find ore deposits is changing, and it has been changing through the years. And I like to think that as we start to add on here and we get in the next 5 to 10 years here, you will start to see hopefully another category here that's entitled spectral or hyperspectral core imaging. But we'll see. Right now we generally get lumped with geochemistry, which you see has been increasing. And we are a form of geochemistry. We're also a form of geophysics, really, if you think about it. So really, the basics of this is that we're looking, exploration is a pattern recognition process. And we're just trying to be able to pick the patterns that mean gold or copper better and faster and more consistently. And if we're able to do that, and we're able to do, in this case, mineralogy better, because that's mainly what I'm talking about, then we're able to fundamentally create these better models that are going to underpin the exploration models, which then get brought over further into the full development cycle. And if we're able to do this earlier and better and more consistently, then we're going to have more success. So, drill core logging. The other half of this, why would you do this? Well, some of this is probably slightly duh statements here. We spend a lot of money on drilling. It's one of the most significant portions of a mining company's budget or an exploration company's budget. So we spend all this money on it, and yet we oftentimes don't treat it very nicely. And we oftentimes have our less experienced geologists log it. And so it's sort of counterintuitive to how important this is. There's also just some inherent things about the fact that geologists tend to be a bit subjective. So there's inconsistencies between geologists. There's also a lot of subtle features that we just aren't capable of identifying. And it is extremely time consuming. So if we start talking about a value judgment here, a value cost judgment here. Because of course, this is how we think our core is going to be stored, how we want it to be stored. But in fact, a lot of times this is what happens to our core. And everybody here has seen this. And we see a lot of it. So I put up here just this idea of the whole mine cycle. Of course, right now I'm going to show you an example that's from this side of things, from exploration and evaluation. But of course, mineralogy is the key thing that goes through this entire cycle. Why don't we get it right first? We get it right in the beginning, in the exploration phase, and we can carry it through all the way. And one of the ways to do that is with continuous hyperspectral core imaging. So there's a whole process here. It's not just the scanning and the logging. You have to interpret it, and you have to be able to visualize it, and then you have to be able to integrate it and help people be able to integrate it. So it's not just about us scanning things and handing you a hard drive. We have to do all of this in order to help our mining clients be able to use this better. So this is a CORESCAN system. I won't go too much into this. I'll just point out that it's got a 50 micron camera, and concurrently being measured at the same time is the HYPERSPECTRAL, which is 500 micron, and also the laser profiler, which is measuring the surface of the core at 20 micron. And you can see some images here of some of the mobile systems. We can measure anything, these core imagers, as long as they don't move, we can measure it. So whole core, split core, chips, cuttings, blast hole, hand samples, whatever you want to stick under there. So this serves also to show you the rest of the products that I'm going to show you from the case study. But I'm showing you a super greenfield sack of rocks comes into CORESCAN type action here. And they want to know maybe they have something here. So I'm showing you a photo here, a class map. So class map is where I've mapped multiple minerals. And then I'm showing you match images for each one of the minerals that were identified in this hand sample. And you can see that this is a match to a spectral library. We use the USGS libraries, so we match against those spectral libraries. We also have a collection of other spectra that we've collected over the past 10 years. So we have about 3,000 minerals and mineral subspecies that we're matching against. We also do a third measurement. This is the laser profiling. I'm not going to have time to talk about this today, but we're doing simple sets of geotechnical extractions with that. Okay, so the case study. As with all technical innovation, it all comes out of Fiji. So we're going to the beautiful island of Viti Levu. And we're going to be here. So we're out here east of Australia. And we've got the two islands here, and there actually are a few deposits. A lot of people are familiar with the Mount Kazi deposit here. We're going to be down here in the south part of Viti Levu, just outside of Suva. We're going to zoom in here, and we're going to look over at this. There's a whole district here, including Waisoi and WAINAULO are the two main deposits. And we're going to focus in on this one in particular, although Newcrest actually scanned core from Waisoi and WAINAULO. Zoom out really quick back again, just to kind of give you a feeling for where we are. Highly tectonically active here. This is one of the most complex tectonic regions on Earth. And it's a great ore deposit nursery here because of that. You've got a lot of volcanoes, a lot of hydrothermal circulation. Again, we're just going to sit right down here, so we're sitting in some of these younger volcanics. And this has created quite a few styles of deposits, even on little Viti Levu. You have quite a bit going on, but again, we're going to be down in here in some of these calco-calcic porphyries, but of course you've got the associated epithermal and skarns associated with it. And then one more background slide. Here we are again. We're going to be looking at this WAINAULO. And just to point out that most of the rocks I'm going to be showing you, the original lithologies of this deposit, are Miocene volcanics, volcaniclastics, and then of course the mineralized dioritic porphyry coming in. So this happened back. We started talking to Newcrest in 2010, and it was mobilized in 2012. So this is the very first project. I'm showing you almost first light data. So this was the very first time we ever brought it to a site and did a large volume of scanning. This was Newcrest proof of concept. They had a couple of things they wanted to try out. Can they use it to improve their geological and resource models? And one of the ways that they hoped they could do that was to make their loggers better. Can we augment our loggers? Can we assist them in some way to make them more consistent and better? And they coined this phrase of calling it core shed petrography. And so what you're looking at here is, again, this is original data. The CORESCAN imagers now cover all of this. But the original had these thin strips that went down the middle. And they used this, and so this is what you're looking at with the loggers they're actually using on site in order to help augment their logging. And this is, of course, going to happen. Toronto. Okay, so then they also use this to then, and of course I can't go through this. If you want to come to the booth later, it's fascinating. But they used this then, it was a combination of the human logs and then bringing in the CORESCAN system. And it's sort of the merging of the two. You're capturing the geologist's brain, and you're using them to help train and make the logging codes better and more consistent. And so you're going from the original human logs to the CORESCAN assisted logs here. And then this is then folded through the entire deposit. Because I'm only showing you one hole there. And so then this was their vision, was it that it's on site, you have assisted logging, it's building out into a real-time model. They use an Inquire leapfrog synthesis, and you're doing that in sort of 24-hour cycle periods, building out a model in real time. They didn't quite get to this, though clients subsequently, some of our various other clients have definitely gotten to this point. Newcrest didn't quite get to this point on NAMOSI, of course, but this was the vision of what they wanted to do. So let's look at some of the data from NAMOSI, and you can get a feeling for some of the things you can do with the data. So we're looking at core shed right now, which is how we visualize our core data. Here's the drill holes here. We're going to be looking at NVD 007 down here. The hyperspectral analysis that we do, we have our own in-house software that we use called Chameleon. We mask all the non-core material. And then we basically analyze against, as I mentioned, a whole suite of minerals from a spectral library, including from the USGS, for the original identifications. And if I hit, let's see if this works. Yes. So you'll see in real time, this is actually our software, and you can see the signatures updating in real time. So remember, again, we've got 200,000 pixels per meter. And so our spectral geos are going through, they're roaming through here, and you can actually see in real time each pixel has its own individual signature that's then being matched against a library. For NAMOSI, this one, normally a project library, if that was all the geo was doing, takes 2 or 3 days to compute. However, normally in a standard process, it's probably more like 3 to 4 weeks to really define that library and get that down because of all the other things that's going on. But you can see here the minerals that were identified. This probably comes as no surprise, although NAMOSI is an interesting porphyry. It has a few oddities to it. But we also computed various composition images, and I won't go through these because we'll look at a couple examples here. So 2 levels of classification are performed, and as I mentioned before, we do a class map here. So this is all of the minerals that are identified, and again, I'll keep putting this up so you can refer back to it, and then these individual match images. Again, where red is a very good match to the library, blue is a less good match, but still a match, and black is a no match. So I'm going to show you chlorite just to give you a feeling for what we're actually doing, because I'm going to show you a couple of chlorite results. I won't go too deeply into this, but we are keeping track of not just the positions of features such as these, but also slopes, shoulders, etc. And the behavior of chlorites a little less well constrained than white micas are, but there's quite a bit of knowledge about that, and certainly the relative changes in chlorite are very well understood. And so I'll be showing you some results tracking this 2250 feature, which I'll show you actually turns out to be very important. So here's the drill hole. Here's NVD 007. Here's all 894 meters of it, and I know that no one can see that, which is why we're going to zoom in. I'll come back to this right at the end in a couple of slides. But first, let's kind of zoom in on here and look at the those. So I'm going to show you the 4 main alteration stages at NAMOSI that were captured, or that are known, and also how the hyperspectral captures those alteration. So we're going to start kind of small scale, and then look at how we take that information we learn from the small scale and scale it out into the entire deposit and say something about mineralization. So this first one, this is the proximal early phase alteration at NAMOSI. It's not super extensive, and a lot of it has been overprinted. It's hosted within the Pluton and the original vertical stringer dikes that have come off of it. What I'm showing you here, so for the next 4 slides, the alteration that's listed here was actually defined by a recent thesis out of Codes, Orovan 2016. And where I've bolded here is what we used in order to mimic or approximate this alteration phase. It doesn't mean that I can't see some of these other minerals. So for instance, we see magnetite, of course, but what it's saying is that this is what we used in order to reproduce what was currently understood at NAMOSI. But I'm also going to show you some things we found that they did not know. And so I'm showing you examples here of those that were identified. So you're seeing phlogopite biotite, actinolite, and then you see this overprint here already of the chlorite, which becomes very important here. So here's the main stage. So this is when the copper and gold came in. And this was mainly hosted in these quartz magnetite bornite veins, as well as some quartz sulfide veins. And then it was overprinted. Again, this was what was understood by chlorite, albite, quartz, actinolite epidote. And you can see we're capturing that, and we're even capturing some of the original biotite veins here, biotite phlogopite. And you can see that the chlorite comes in, it's pervasive. So, you know, it's not just that we're identifying those, but we're able to very quickly pick out paragenetic relationships here and see what's cutting what. And so we see that the chlorite, though it's dominantly pervasive, it's fairly intermediate in composition, although there are some variations, and that's where it gets interesting. But what we can see here is that it's actually a far more complex paragenesis than was previously understood. And I'll come back to that when we look at the big scale of the final, sort of the answer, if you will. Then there's 2 other phases. So there was a post-mineralization overprint that came in. So this is sort of lumped into generally stuff that's maybe a little less important because it's not hosting the copper or gold, but it's important to know what that looks like and thus where you're going to have more barren rock. One thing I'll point out here, this is a really nice pattern. This is the chlorite, 3? Okay. This is the chlorite composition. And where you see it's getting in closer to this vein here, you can see that it's actually getting, what this means is that it's getting very iron rich. So this is a camosite. And as it approaches the sulfide veins, it's getting very iron rich, which is a nice way to convince ourselves as well that we're seeing true geochemical behavior here. And then the fourth one was the structurally focused. I won't go too much into this. There's a whole other area of NAMOSI that's fascinating because there's a lot to do with mineralization and the big faults that cut through this area. And so there's some really beautiful alteration associated with the structure in this deposit. And we're able to capture all of that quite well as various orientations of fractures. So let's zoom out to like here. This was the real takeaway, the final piece of this that made all of this worth it for the NAMOSI deposit. So now we've zoomed back out. We're looking at about 50 meters of core here. We're at about 600 meters depth. Here's a class map. Now what you see here is Newcrest assay. I've made it very tiny so you can't read the numbers, but you can see relatively as we get into red and purple, we're getting higher values of both copper and gold. And we start to see even just visually, you should be able to pick out that as we start to increase, let's particularly pay attention to the copper. Right before you start to see increasing copper grades, you see some really beautiful relationships here where all of a sudden the montmorillonite starts to come in, and kaolinite, gypsum, actinolite, and it's immediately preceding this high copper zone. In fact, it's quite a sharp boundary. The other thing is that, so Oravan noted that, he noted what I'd mentioned before, that mineralization was hosted in this chlorite, albite, epidote, calcite zone with montmorillonite, but he also noted that the actinolite increases in the copper zone. And while we see actinolite, I know it's very hard to see, you're going to have to trust me that there's all sorts of little dots in through here of actinolite. What we noted was that, in fact, rather than, I'm getting ahead of myself, I think I actually made some points here. While we do see exactly what he said that was understood, and by the way, I should say, I'm quoting Oravan here. Newcrest knows a lot more, but it's easier just to talk about what the graduate student did. So there is more information than this, but we're sticking with the grad student, the public data here. So while we see this decreasing montmorillonite and epidote as this main ore zone is approached, and that's really important, and it helps us really define those alteration shells, we also see a really strong response from the actinolite immediately preceding the ore zone, and then it drops like a rock as soon as you get into the copper zone. So that's actually quite different than what had been previously thought. And what this allows them to do was to discriminate copper-associated actinolite from barren actinolite. 1 minute. And this was really important because for quite a while at NAMOSI, it was really just actinolite was a vector. Like, oh, if you have actinolite, you have copper. And so this was able to really refine that. So sharp boundaries there, already talked about that. And then the final piece, chlorite composition. So the chlorite is sitting in the ore zone. And you can see that while there's a lot of it here, there's really some interesting compositional features coming in. So we take all of that imagery data and we put it out into point logs. These are CSV files. They go directly into any 3D modeling software, geostatistical software you might have. Oops, oh, that didn't work. There's supposed to be a really cool model that builds out here. They told me it would go. If there is a guy running it, they could hit the button. But so what this basically shows is that what we found is that the chlorite composition, as it becomes more iron-rich, is just an absolutely beautiful vector for copper. So it's not just do I have chlorite, it has to be the iron-rich variety. And it has just this gorgeous correlation with the copper grade shells. So in summary, some of this is from Newcrest, some of this would be from me, but they would say that this improved to their cycle times. It broke the chains of this production-style monkey logging, that it allowed them to do in-core shed project alteration validation. It allowed them to construct first-pass testable cross-sections in 2 or 3 days. They were able to not only validate what they previously knew, which was great, including being able to match their copper grade shells also with biotite, but it also identified several things, including a few vector minerals that they didn't previously know about, the iron-rich chlorite, and also the kaolinite hadn't even been in their logging codes previously. And so I'll end with this, which is sort of the basis of how you bring core imaging into your mine cycle workflows, whether it's from the beginning in exploration, but then moving out further into the full